Hello fellow skeptics, I'm Luther Name, and this is the 16th video in a series addressing the broad topic of, is something wrong with modern physics? If so, what? And can it be fixed? Now, in preparing for this video, I went back and reviewed my prior ones, which is what I typically do for ensuring that there's continuity and clarity in all the points I want to make. I found that it was probably worthwhile putting a review together that basically summarized what I covered in the prior two videos on the Doppler and the aberration effects, both of which were described in Einstein's seminal work on special relativity in his 1905 paper. Now, what I've done is, in this video, basically I put together a more extensive set of visual representations covering the same topics as in the prior two videos in order to clarify and make sure that there were no misunderstandings in terms of what was intended. Because as the point I've made so far is that the Doppler and aberration expressions are in fact what special relativity is all about. The kinematic part, which was emphasized by Minkowski's reformulation, doesn't exist. It's a fabrication. And all the things that occur within the kinematic part of the 1905 paper can be explained with respect to how electromagnetic radiation is used to either measure or accelerate particles. With that, let's get to the visual materials I prepared, since they take up the bulk of this particular video, as do my explanations and discussion as I present those visual materials. This little addendum is to indicate the reason it took so long from the prior video to release this video, even though this one is only a refresher. I violated one of the basic rules of project and program management, or management in general, which is scope creep. As I began to look at certain facets of the Doppler expression, and like with the aberration, I tried to put some examples together to scope out the magnitude of the effects that we're looking at. And what I realized was that I got interested in it and drag things out. The cardinal sin of any type of program management is scope creep. And in my case, the scope created that was increased was a result of becoming interested in some things, namely the Doppler expression. I began to realize that almost nobody had looked at it in any detail. We have some indications through our movies and television and things like Stargate, how the star fields change as a result of motion through these gates. Star Wars itself, the so-called jump to light speed, and you see it in other movies, Star Trek, what have you, and these are artists' renditions. And I began to realize we really didn't have a good handle on what actually the Doppler looks like. There are various phrases. Roger Penrose in pre-computer days made some calculations, but I'm not sure how accurate they were. I've not been able to find these predictions to go back and assess them, and I realized that there was a lot more work that needed to be done, and it was not just a casual thing like with the aberration effect itself, but I was going to have to dig back into Mathematica, and there's a learning curve, and I didn't really have the time to dig into it at the moment. I will in the future, and so outside the scope of this particular series of videos, which are basically just to tell you the kinds of things to look at, to create a guidance in terms of what to explore and how to explore it, as opposed to actually doing the work. Again, cardinal sin, I got interested, scope crept, time passed, and you can't let scope creep. So with that, let's go ahead and get to the slides. In this series of slides, what I'm going to do is to reiterate details of what I've stated before, but how to use these actual equations. You can't use Einstein's equations, and these come from his 1905 paper. You can't use them directly because Einstein did not consider any of the details associated with scenarios and the actual physical act of measuring. He simply said, well, somebody sees this or somebody sees that. You really have to know how they're looking at something, how they're measuring something. And Einstein didn't do that. And again, my point that I made earlier was that these equations from the electrodynamic part of his 1905 paper really can be used to fully explain everything, whether he got it right or wrong, in the kinematic part. These equations can be used to explain everything that he claims occurred almost spontaneously at high speeds in the kinematic part of the paper, which he got wrong. This is special relativity. Now, in looking at these and paying close attention to how to use these equations, I had to build scenarios. Well, I wound up going through down a couple of rabbit holes, and it took longer than I had expected, which is the delay between some of my prior videos and this particular video. I had to go back. I overlooked something, and I had to go back and correct and make sure I hadn't made a similar kind of error earlier in what I was doing. I had not. And so what I'll do is I'll show you where I made a mistake and how to correct it. But still, none of it negates the fact that the kinematic part of Einstein's paper just simply doesn't exist. This, from the electrodynamic part, is what special relativity is all about. And so one of the things, just to reiterate these equations, here's an observer moving in a particular direction. Here's some radiation coming in obliquely to that direction. These are considered to be plane waves, and this is a normal to the plane wave, which we call rays, because they just, in the geometrical sense, this is the direction the radiation is following, and we call them rays until we use a different form of the electromagnetic radiation equations, and we get a plane wave, which is defined with many of the same elements. The object, we're moving through the radiation at an angle phi, but we have an angle phi prime, which represents what we actually measure. This is the difference in all these equations. Notice that if we want to find what the frequency shift is, it asks for cosine phi. In reality, we can't just put in cosine phi. We have to put in phi prime to capture the effect of the aberration. Well, that means that we have to change this equation into a phi prime equation. This is how we do it. So Einstein's equation is repeated here. One thing to note, though, is that when phi equals 0, then phi prime also equals 0. So that when we're looking at something like a radar, what we get is a simplified version of this Doppler equation, and it's the same regardless of whether we use phi or phi prime. Again, this is just the same equations. Here's what we stated on the last slide. When phi equals 0, phi prime also equals 0, and we get this simplified form for the Doppler equation. The same is true as if we're moving into the direction of flux as opposed to moving along with the direction of flux. And what we get is another very simple equation. Another situation that occurs, and we showed that in the last video presentation, when a telescope is looking at the sun. It could be looking at any object from Earth's orbit, but when we specifically look towards the sun, then we have phi equals 90 degrees. Now, phi and phi prime are definitely not the same. They're different. And when we look at phi equals 90 degrees with the look angle, what we get is this form for the Doppler equation. To reiterate, when we expand this using a small beta approximation, this is what we get for the Doppler. Doppler is the difference between the two. The Doppler shift is the difference between these two frequencies, the original and the shifted. And what we get is a bias, a permanent bias on the order of beta squared, which is positive. This is the prior slide repeated, but with the added note that the form for the Doppler in this particular case is wrong, because the equation for nu prime, the shifted frequency, does not include the fact, in this particular equation, does not include the effect of the aberration. So how do we fix the situation? Well, it's actually pretty straightforward once you recognize what you have to do. This is Einstein's aberration equation. It contains phi as opposed to the aberration angle phi prime. Solving this for cosine phi, which is what's required in his Doppler equation, we come up with this. This is cosine phi in terms of the measured values of phi prime. This then is what is put back into the Doppler equation in order to insert the effect of the aberration on the frequency. So carrying out that substitution, here it is again. We have cosine phi as a function of cosine phi prime. Substituting in the Doppler equation, which is this equation of Einstein's that does not contain the aberration, this is what the Doppler equation looks like with the proper substitution of cosine phi prime. Phi prime, again, is what we actually measure. This is the summary of what we've just been talking about in the last few papers. And so this is ultimately using a small beta approximation for the types of observations and scenarios we've discussed so far. This is now what the Doppler equation really should look like and that should be used, as opposed to this particular equation, which gives the wrong answer. Using this small beta approximation with the aberration included, this is what we have as the way of the Doppler shift. And at phi prime equals 90 degrees, such as when we're looking from Earth to the sun, this now is the actual Doppler shift that occurs in the radiation that would be measured. So what do we really have here? We have not only that the frequency is changed by the aberration angle, the aberration angle itself is just that. Instead of having the radiation follow the normal geometric paths of propagation in a system where there's reflection, what we have now is a deviation in the actual path of the radiation. And it's given by this relationship. Phi prime is related to phi by this factor. We call it small delta subsequently. And this is, again, a small beta approximation for what the actual change in the angle of the radiation is after interacting with materials. In the small beta approximation, when cosine phi prime is close to 90, when viewing the sun from the Earth as a particular scenario, the Doppler equation is, as we stated, given by this. However, we can modify this to get a more precise reading of exactly what the Doppler shift would be when looking at something like the sun. In the prior video, that's exactly what I posited and calculated. However, I didn't use the correct equation. And the reason for that is that when you recast those equations in phi prime in terms of a small angular displacement from the phi prime equals 90 degree observation angle, we can find that angle with respect to the center where phi prime equals pi over 2. And we then have, when we convert the this equation in cosine phi prime to a new parameter called lambda, which is a small angular deviation relative to the 90-degree position, what we find is that this deviation is on the same order of magnitude as beta. This
was overlooked. And with the fixation on a small beta approximation, it was overlooked that cosine phi prime in certain scenarios itself will be small, and in the case of the observation of the sun, it's on the order of beta. So what we have is another term that's on the same order of beta squared that was omitted from the analysis. This is from the prior video where we're looking at observing the sun from the Earth, and we discussed that. And as we look at the sun, as we scan across the sun from limb to limb at the equator, the deviation of the Doppler, of course, there is no Doppler at an offset angle of beta over 2, followed a curve similar to this, but that's incorrect. What happens when you include the term that was omitted? Again, cautionary tale. Don't get fixated on what you think are large and small parameters in any given scenario. You have to look at the scenario and you have to evaluate the terms so that you're making sure that if you're going to use any approximations that you're being consistent. I was not consistent, and when I put that value back in, we now get this linear description of what the Doppler is. It goes from being a positive Doppler to a negative Doppler as you scan across the sun. And going back and looking at some of the data that I was trying to match the original curve with, it was really very crude data, and by today's standards. And I haven't found any modern efforts to duplicate that work. They use small aperture telescopes, collect the spectral data, because they didn't need to have large apertures because the sun's so bright. When you're looking at stellar objects outside the solar system, the light is so dim that you need a very large aperture to capture enough light to be able to make your measurements. So when they were looking at the sun, they were looking at a very large aperture. Instead of a small spot, it was a very large spot. And so the data was very crude. It was hard to see what was happening. It was definitely varying from limb to limb, but there was only occasionally a hint of the fact that there was no Doppler at a particular offset angle. It was very small. And so this is what the correct change in the Doppler would be as you scan across the sun.
I made a decision to cut this particular video a little shorter than normal. It was getting long, and I don't like to make them much over 20 minutes long. That's a pretty long attention span for these kinds of things. So I cut it, and what I'll do is in video 16 is really a continuation of video 15 along the same tracks of the showing how to use the equations and what the effects are and the kinds of scenarios and analysis that can be made. But again, I'm just cutting it short, and that's kind of an arbitrary decision as I saw how long it was getting. So as you can see, the prior slides, there were a lot of them. I put them in and ran through them pretty quickly because I wanted them to be there as reference for anyone who wants to dig into this. Again, the original scope and the one I tried to adhere to is to show how to use these equations, the proper way to use them, things that had been missed or omitted. The goal wasn't really to do all the work. There's time for that. I will have a series of videos after I'm finished with this series on modern physics to just discuss some elements of the science and technology, including the Doppler shift itself, to try and supply some clarity to what the artistic representations ought to be, and also to address other anomalies, things that have kind of troubled me a little bit in terms of what we think we're talking about in terms of the applications of some of these scientific elements and to various technologies and the kind of technologies we might be looking at. Simple things like communicating with a space vehicle that may be moving at a large fraction of the speed of light. How would we do that? Why would we do it? What would be the consequences? And this all was part and parcel of how do you measure things. What are you looking at? What are you seeing? How do you interpret what you're measuring? So I'm going to get into that a little bit more, but not here. And not in this sequence of videos. So with that, again, thank you for watching. Subscribe, leave a comment, and I'll see you in the next video.